Welcome, I'm Maciej, and I would like to present our recent results into dynamic graph representation learning. This work was published at the last year Learning on Graphs conference. We are going to focus on the link prediction problem. So in this problem, we have some given graph data set that we can use to model, for example, social interactions or biological interactions or anything else. And we are asking basically a question on the future of this data. So we would like to understand with high certainty which edges will appear between which nodes in this graph. We care about that problem because it's a very important problem that we can use to basically predict the future of this data. Right? So this enables better analytics, better scheduling and management strategies, etc., etc. We are also going to assume that we have access to the history of past updates, right? So that's where this dynamic adjective stands in the link prediction formulation. So by saying dynamic link prediction, we mean that we have access to the history of past updates, right? So the graph is dynamic, is sitting in a dynamic setting with new edges coming and going, and new vertices coming and going, and we know what was going on in the past. Now, most schemes out there use the following type of strategy. So if we have these two vertices U and V, and we would like to understand if there's going to be an edge between them, in many of the schemes out there, we analyze the overlaps of the neighborhoods of these two vertices, right? So now, depending on the size of this overlap, the chance for this edge to appear can be either higher or lower. So these are, for example, Jacquard, the established Jacquard and common neighbors coefficient scores, which directly use the size of the overlap, give us the score for this edge to appear or not. There are more such schemes, and all of these schemes basically rely on in one way or the other on simple dyadic edges, right? So it's kind of obvious because, well, we have a graph data set which means we have vertices and edges between two vertices, right? So one edge only connects two vertices, so it's kind of natural that we consider these simple dyadic edges. Well, not completely. So our idea was to harness so-called higher order graph structures to make these predictions, to make them more powerful, more accurate. So an example higher order structure is a well-known triangle. It's a triangle, so it's basically a free cycle. It's a cycle between three vertices, and but you could also think of this triangle as a sort of special type of not really edge, but some other higher order edge that connects three vertices at the same time, right? So that's one thing we are going to focus on, how to use such structures for more powerful predictions, for link prediction. And also, this naturally means that we are also going to consider higher order neighbors of vertices, right? So now if we have these two vertices here that we would like to understand whether they will be connected with an edge, we are going to consider these higher order structures, and that implicitly means we are going to consider also their higher order, for example, two-hop neighbors. So why do we care about this higher order in the first place? So there are tons of works showing that harnessing higher order graph structures makes different types of predictions, different types of models more powerful. So there's a lot of works out there about that. I'm only here showing you one example from AAAI 2019, but there is a lot of these works that are universally showing that once we introduce higher order, we have better quality of predictions. So before we proceed, let's first take a look at what precisely higher order actually is. Because I'm just speaking about triangles, but let's take a look at this in a more broad, from a more broad perspective, because higher order is a very, very broad concept. So intuitively, it means really anything that goes beyond a simple dyadic edge, right? So in this example graph here, we can see like a simple graph, a plain graph with just dyadic edges. But now, one way of introducing higher order is to use a hypergraph, where instead of these dyadic edges, we have hyper edges, which are basically edges that are modeled with subsets of vertices, right? So now an edge can cover multiple vertices. Another way to introduce higher order is to introduce so-called node tuples. So now we have tuples of vertices that can be seen as a kind of hyper edges with inner ordering of the vertices imposed, right? So now we have these tuples, they connect these vertices in the ordered way. We can also reason about the connectivity between these tuples themselves. We can also use in a similar way subgraphs, so we can basically specify some distinguished subgraphs that we basically see as a sort of higher order connections, right? So we could now see these subgraphs as a sort of hyperedges with some inner structure. Again, treating these subgraphs as the way to connect these vertices. And then we could even order these subgraphs using subgraph tuples, similarly to node tuples, an even more powerful way of introducing higher order. And then models out there that are basing on these structures are usually even combining these notions. So, for example, quite a common way to combine these structures is to combine simple dyadic edges with node tuples, with subgraphs, and with subgraph tuples. So in this work, we are going to focus to a certain degree on the higher order introduced by subgraphs, by considering subgraphs and combinations of subgraphs with edges. However, if you want to learn more about these higher order structures and also neural models that are harnessing these higher order structures, feel free to check our paper called Demystifying Higher Order Graph Neural Networks. So you'd like to harness higher order, fine. So let's start with the overview of the whole pipeline that we are going to use here. Right. So the pipeline consists of three steps. In the first step, we need to extract the relevant higher order structures. In the second part, we need to encode the structures in the way that is suitable for making predictions. In the third part, we are going to make the predictions. So when extracting the relevant higher order structures, what structures do we actually care about? Right. So we are going to care about not just plain higher order structures, but something we call temporal higher order. So let's understand what this temporal higher order means in the context of this example here. Right? So we have again some example graph with two vertices u and v, and we would like to know whether these two vertices will be connected at some point. Right? Here we have our timeline. Right? So at some point in the future, there may be some new edges coming. So there may be these new green edges, the one here or the one here that we insert at a certain time. There may be more new edges. Then at some other timestamp, there may be some edge that is going to be removed, which we indicate with this dashed red line here. Then more edges may appear, etc., etc. Right? And now, one way to harness the higher order is to basically mine for and extract these higher order structures, for example, triangles, from each of these timestamps, right? So we could, for example, try to use the higher order structures that we see in this timestamp here. So here you can see, for example, a triangle. Here's another triangle. However, what we are going to do in this work in our hot model is basically also considering temporal higher order structures. So we can see that if we now consider these three different timestamps, we could see that there is a triangle that is sort of spread across these three timestamps. Right? And we would like to consider these higher order structures as well. That's what we are doing in the first part of the pipeline. We mine for these patterns as well. And basically, all these types of higher order structures, and including the temporal ones, basically will help us to make more powerful predictions. For example, in social networks, a triangle appearing among the neighbors of two vertices makes it probable that these two vertices will become connected in the future. So we will consider all these things in the predictions. Now let's take a look at the rest of the pipeline. Well, how we encode these higher order structures, how do we build the model and make the predictions? Let's start with the formal setting before we proceed. So in the formal setting of the model, we assume that we are using the continuous time dynamic graph, in short CTDG, which is a well-known established representation for dynamic graphs. It's the one that we use most often these days. It's formally a tuple G0T, where G0 is the initial state of our graph. So G in general means a graph here, and we model a general graph as a tuple consisting of a set of vertices V, set of edges E, and F and W that represent our feature vectors that we assign to vertices and to edges. And then the 0 indicates that we just consider the initial state. Now, the second part of the whole CTDG representation is T, and T is basically a set of tuples of the form timestamp event. Right? So this is our history of updates. That's what we use to model all the events that the graph has witnessed and their corresponding timestamps at which these events took place. Right? And now, in the dynamic link prediction problem, we assume that we have some representation, some data set modeled with CTDG. So we have this G0 and T. We have some given timestamp T, and we have a given edge U and V. And we are basically asking a question on what are the chances whether at a given timestamp T, there is going to be an edge between these two vertices U and V. Right? So this is also the way to state this formally is to decide whether there is some event E pertaining to this edge U and V, or these two vertices U and V, such that this event takes place at this timestamp T, and while considering the history of the past updates, right? So this is the formal way to state it. We don't have to actually take a look at that in more detail. What is important is this intuition, right? That we have a timestamp T that is a given, we have an edge that is given, and we would like to know if this edge will actually materialize while considering all these past updates that we have within our CTDG. So here is the overview of the hot model architecture. It looks a bit complicated, but let's go through it step by step. And really, this first part here, the 3.1 part, is really the one that we already briefly mentioned. It's basically mining, extracting these higher order patterns. So in that part here, we are basically taking these vertices and we are mining for their higher order neighborhoods, and we are finding these higher order structures that we pre-selected. So this is a sort of hyperparameter, which of these higher order structures we are going to harness, and we are going to mine for them in the first part of the whole pipeline. What then happens is that this stage outputs these two matrices. For each of these two vertices, V and U, we are going to obtain these two matrices, SV and SU. And basically, these matrices can be seen as very tall matrices. So each row is basically some past interaction. So we order these interactions, and this is why these matrices are so tall, because we have usually a rich history of these past interactions, and each row is a single interaction. Right? So the whole matrix can be seen as a historical neighborhood of vertex V encoded as a matrix. Right? And each of these rows is basically the ID of the source vertex, the ID of the neighbor that this interaction, for example, like insertion of an edge or something like this, was happening, and also a given was happening together with, and then the timestamp that this event happened. Right, so that's what each row of this matrices means. And this is it's important to realize that at this stage we already mine also for higher order neighbors. So this neighbor ID could be a second hop neighbor, could be a third hop neighbor. So depending again on how you select this, how you pre-specify this. Then we construct input feature matrices, because in this S matrices we have only the row structure encoded, but we now also need to throw in some parameters and to have some features, right? So that's what we do in this block 3.2. We output these matrices. So the X in that case Vn is a matrix that basically comes with now vertex features. So this is the matrix that again, each row corresponds to a past interaction, but now these rows are basically vertex features, right? So we can now have a way to parameterize the model. And then we also use one-hot encodings in addition to indicate if these interactions are single hop, two hop, or some other k-hop interactions. We do something similar for edges. So we also have edge features in the matrix also to be able to parameterize the edges. And then we also need to throw in some time encoding, right? So this is also what we need, because we're going to use transformer in the following part to make the prediction, and this is why we also need some time encoding to make the transformer aware of the time, right? So we have these three matrices that we spit out from that part here, where we construct the input feature matrices. At the same time, we're also encoding the higher order structures themselves, right? So these S matrices and these X matrices sort of already consider higher order neighbors, but these are just neighbors, right? So we also separately encode the structures themselves, like triangles or some higher order cliques that we may have pre-selected. So these are included in these matrices X, U, and C. So basically, these are simple matrices. These are quite simple matrices, and all they do is encoding what is the shared counts of neighbors between different vertices. So if we would like to encode triangles, for example, all we need to encode is to encode shared vertices between these two V and U vertices at different points in time. So that's what basically these matrices are doing here. Then we take all these matrices we constructed and we sort of combine them together in a three-stage process. So this three-stage process where we have these steps of patching, alignment, and concatenation is basically what we are relying on. We are relying here on past work. So this is the so-called DyGFormer model that we are harnessing here for these optimizations. It's basically reducing a bit of the memory pressure. So patching is for each of these matrices, so this XUC and all these others separately, we take these matrices and we apply patching, which basically means that we divide the number of rows by 4, and we at the same time increase the dimensionality of features by 4. So this is like a way to, or this 4 can also be some other factor that is selected. This is also a hyperparameter. So that means that we are going to reduce a bit of the memory pressure because the history may be very long, right? So this is a way to deal with the very long histories. Then we are applying alignment, which basically means applying some down projection to this potentially very large dimensions to make them a bit smaller. And finally, we concatenate all these matrices together to provide a single input that we are then feeding to the final part, which is the transformer, right? So now we have some concatenation of all these matrices that in some way encodes all of these past interactions and all of these higher order structures that we harness, that we extracted from this history. Now we feed this to the transformer. But now the problem is that there is one big challenge, and this is also where this efficient transformers kick in, right? So this part of the model is basically a black box. So any transformer could be used here. We are treating a single interaction as basically an equivalent, intuitively speaking, a sort of equivalent of a token here. So all these past interactions are talking to each other now in the transformer model. But now the problem is that once the history itself of all these past updates may be a long one, right? So this already makes it challenging to stuff all of these updates, past updates in the transformer, in the attention matrix. But when we harness additionally higher order structures, that makes this history potentially blow up even more in terms of its size. So that makes it even more important to try to find a way to reduce memory pressure. And we use it by plugging in a selected efficient transformer. So a family of so-called efficient transformers is basically a rich family of models where we try to somehow reduce the memory pressure from the attention matrix by, for example, applying sparsification. There are many of these schemes. In our model, we selected a specific variant called the Blach recurrent transformer, which fixes two things. So on one hand, it combines basically the standard attention with standard recurrent neural networks. And now the problem with the standard attention is again that we may need a lot of storage. In the RNNs, of course, we cannot model long histories because RNN will not be able to deal with long histories. But this is what Blach recurrent transformer does, basically by providing a trade-off between these two. So it's like you could think of this as a sort of higher level RNN where each cell is a small scale attention. So you plug in this model, and actually the results are pretty good. So let's take a look at some evaluation. Here in this data set, on the left side, we are comparing the AU score. We are comparing the accuracy score of a couple of different comparison baselines. So the colors of the bars correspond to different models. The darker is our hot model, and all others are written down here. And for each of these points on the x-axis, we are comparing different sampling strategies that we use in training, sampling strategies for picking edges, and also different accuracy scores. So we use, for example, AP, but also the other one. And we also consider the transductive and the inductive setting. Right, and we can see that we consistently outperform all the other models by a certain margin. And also to delve a bit deeper into these numbers, we also analyze specifically the difference in performance for us between harnessing only one hop and one hop plus two hop neighbors and corresponding higher order structures. And we can see that using higher order here really does help. We have more such positive results in the paper, but we also have some other which are quite interesting from a different perspective. So here, the same setting, we have again the accuracy scores compared, different sampling, different scenarios here, different models correspond to different colors of bars. And now what we can see is that while for that data set we are still better, however, if we now plot in more detail what higher order structures we are using, we are seeing that harnessing these higher order structures doesn't necessarily help too much, right? So basically, if we just plug in one hop neighbors, we are basically outperforming cases where we plug in the higher order neighbors. Right, so this is one specific example I want to use here to illustrate that this higher order might also be a bit challenging to use, and you may want to understand the data set better, because maybe the data set has some noise, and then if you harness more of these structures, you might actually be getting more of the noise into your model, right? So that's what you would like to avoid. However, overall, the model does very, very well. So that's it. You can find more analysis, more data, more details of the model in our paper. Thank you for your attention.